Section 4.4 Coordinate Systems. In general, we're more comfortable working with a vector space Rn and the subspaces that come with it than with other types of vector spaces and subspaces. So what we're going to look at in this section is how we can impose coordinate systems on vector spaces even if they're not in Rn. So starting out here, having a basis beta for vector space V essentially sets up a coordinate system for V. If beta contains n vectors, then this coordinate system makes V, our vector space, act like Rn, even if it's not Rn. So let's look at this theorem and definition. Theorem 7 is the unique representation theorem. If we let beta be the set containing these vectors b1 through bn, and it's going to be a basis for the vector space V, then for each vector x that's in that space V, there exists a unique set of scalars, C1 through Cn, such that we can write x as a linear combination of those vectors in the basis. And we see it written there. Now this definition says if we suppose that this beta is a basis for our vector space V and x is our vector that's in V, then the coordinates of x relative to the basis B, okay, or we shorten this saying the beta coordinates, B coordinates of x, are the weights such that we can write x as this linear combination of our vectors from the basis. And we write this using this notation. So this kind of stands for the B coordinates of x. And the B coordinates, notice it's a vector here of our weights C1 through Cn. This is the B coordinate vector of x, or the beta coordinate vector of x. Now let's look at this example. In R2, we're going to define B1 and B2 here. And then we're going to say that beta, or capital beta, is this basis that contains those two vectors, and it's a basis for R2. So we want to suppose that our vector x has the B coordinate vector given here, -2, 3. And what we want to do is find x. So we see here that our B coordinate vector was the vector -2, 3. So we can write x then as -2 times b1 plus 3 times b2. So I have -2 times 1, 0 plus 3 times 1, 2. And when I work that out, I will get the vector 1, 6. So that is now my vector x. And here we're going to look at the regular graph paper with the beta coordinate graph paper laid on top of it, so you can kind of better understand how this fits together. So we have B1 and B2 vectors. So here they're graphed. B1 was 1, 0 and B2 was 1, 2. And then our B coordinate vector, the -2, 3. So we're going to draw the B coordinate system in red, and we want to plot x. So in red, on top of our other graph paper, the normal graph paper, we have the B coordinate system. And see here, we've just erased the other graph. And we have x is -2 b1 plus 3 b2. So we're going to take B1 and we're going to go back 2 spaces, and then we're going to take B2 and we're going to go up 3 places, and we see using B coordinates that x is up there. Now what we did in the previous example, using these exact 2 vectors, we found the coordinates for x was the vector 1, 6. So let's put our graph paper back, and we see that if we look at it, going over 1, and up 6, x is in the same place. So this is just a demonstration that we are alternating from our regular coordinate system to our beta coordinate system, and we end up with the same thing. We end up in the same location. So bearing that in mind, we need to ask the question, how can we change from one coordinate system to another algebraically? In the previous examples, we've been given our b coordinates, and so we had to then find our vector x. But now, how do we find those? So changing from the b coordinates to the standard coordinates is easy. From the last example, we're going to let p sub beta be equal to the matrix that has those vectors b1 and b2 as the columns of our matrix. So we'll end up with this 2 by 2 matrix, 1, 0, 1, 2. Then if I multiply on the left by that matrix p sub beta, we change our b coordinate vector into our vector x. That is, we have p sub beta, our matrix there, multiplied by our b coordinate vector will produce our vector x. So here's our equation set up where this is our p sub beta, the matrix that we just came up with. Here is our b coordinate vector, and here is the vector x that we came up with. And you can check to see that when I multiply across and down in both and add those together, then I will end up with this vector x, so that this equation is true. This p sub beta, the special matrix we came up with, is called the change of coordinates matrix from beta to the standard basis. So in general, for our vector x, which is a linear combination of our vectors b1 through bn, we have this equation here. So this is basically written in this way. If I pull out my coefficients c1 through cn, then what I have is the vectors b1 through bn multiplied by those coefficients. And so we see then that that is equal to p sub beta, the change of coordinates matrix, which we have here, this b1 through bn, the matrix made up of those vectors, multiplied by the weights in our linear combination, which was the b coordinate vector. So now let's look at how we go from the standard coordinates to the b coordinates. There's a little more involved here. So since we found this equation, we could multiply on the left by the inverse of our change of coordinates matrix, p sub beta, and end up with this equation here, that our b coordinate vector is the inverse of the change of coordinates matrix times our vector x. We need to note that our change of coordinates matrix is invertible since its columns are a basis for our n. So let's look at this example here. We have b1 and b2 defined here, and we're going to say that beta is the set consisting of those two vectors, and our vector x is this vector 6, 8. We want to find the change of coordinates matrix p sub beta from b to the standard basis in R2, and the change of coordinates matrix p inverse beta from our standard basis in R2 to beta. So the first thing we're going to do is we're going to find our change of coordinates matrix and then the inverse of it. So p sub beta, remember, is just equal to the matrix made up of b1 and b2. So it's going to be this matrix here, 3, 1, 0, 1. So that's fairly easy and straightforward to find. So here is p sub beta. But now we need to find the inverse of that. So what we're going to do is we are going to take the determinant, which will be 1 over 3 minus 0, so we have 1/3, times 1, 0, negative 1, 3. And so then we have 1/3, 0, negative 1/3, and 1. So then this is the inverse of our change of coordinates matrix. So the second part of this example is given our vector x, which was equal to this vector 6, 8. What we want to do is we want to use our inverse to find our change of coordinates vector. So the change of coordinates vector is going to be equal to our inverse of our change of coordinates matrix times our vector x. So we're going to take then 1/3, 0, negative 1/3, 1, and multiply it by x, which was 6, 8. Remember, you're going to go across and down, and you will end up with this vector 2, 6. And so that is the b coordinate vector. And that is how we can change from standard coordinates to the b coordinates. Coordinate mappings allow us to introduce coordinate systems for unfamiliar vector spaces. So in this picture, excuse that it's not very clear, but in this picture we have a vector space V and we don't really know what it is, and some vector x that's in it. If I multiply by the beta coordinates, then I am mapping from V, whatever our vector space was, onto Rn. So let's look at another vector space other than Rn that we're fairly familiar with. The standard basis for P sub 2 are polynomials, which is the vectors P1, P2, and P3, where P1 is 1, P2 is t, and P3 is t squared. These polynomials in P2 behave like vectors in R3, since we can write a polynomial here, a plus bt plus ct squared. We can write it as a times P1 plus b times P2 plus c times P3. And so what we have then is we have a plus bt plus ct squared, the beta coordinates there, equal to just a, b, c, this vector here, which is in R3. So we can say then that the vector space R3 is isomorphic to P2. And this is simply because these polynomials that are in P2 act like vectors in R3. So here's an example. We're going to kind of compare these parallel worlds of R3 and P2. A vector space R3, vectors that are in that form have this form, A, B, C, 3 entries. In our vector space P2, they have this form where they're a polynomial, A plus BT, this is a typo, plus CT squared. When we add vectors in R3, we're adding 2 vectors that have 3 entries, and we produce a vector that has 3 entries. Like we are adding them in the same location. Kind of similarly, if we're adding vectors in P2, we're adding like terms to polynomials that have the highest exponent of 2. So I add the constant terms, I add the t terms, I add the t squared terms, and I produce another vector then in P2. So informally, we say that vector space V is isomorphic to W if every vector space calculation in V is accurately reproduced in W and vice versa. Just something I want to take note of real quick. If we assume that beta is a basis set for a vector space V, then a set of vectors U1 through UP in that vector space V is linearly independent if and only if their beta coordinates, the beta coordinate vectors for each of those vectors U1 through UP, is linearly independent in Rn. So this kind of goes along with these two vector spaces being isomorphic. In this example, we want to use coordinate vectors to determine if the set of P1, P2, and P3 is a linearly independent set when they're defined here. Remember that the standard basis set for P2 is beta equal to 1t and t squared. Now I'm going to write P1, P2, and P3. I'm going to write their B coordinates. So I'm going to change this here. I have then that P1, the B coordinate vector for P1 is going to be 1, negative 1, 0. Okay, and this is using this basis set here because I've got that this 1 times 1 plus a negative 1 times t plus 0 times t squared. That gives me P1. Then the B coordinates for P2 similarly would be 2, negative 1, 1, and that's multiplying 2 times 1 plus negative 1 times t plus 1 times t squared. And we're trying, remember, to get these equations for that P2 is defined as. And now we look at P3. So the B coordinate for P3 will be then 0, 2, 3. So then what I'm going to do is I'm going to set up a matrix with these beta coordinates of P1, P2, and P3 as the vectors in my matrix. So I have 1, negative 1, 0, 2, negative 1, 1, and 0, 2, 3. So then I have this matrix set up here. And what I want to do is I want to row reduce it. And when I do, I will get this matrix here. 1, 2, 0, 0, 1, 2, and 0, 0, 1. So we see then that I have a pivot in every row, and this is a square matrix. So then by my invertible matrix theorem, the set of these vectors, the beta coordinates for P1, P2, and P3, is linearly independent. And that note that we looked at in the previous slide said that if those are linearly independent, then my original vectors, the set of those, is linearly independent. So we were able to show linear independence using the invertible matrix theorem when we were dealing with R3, and by doing that we were then able to show that these vectors that are in P2, that they were linearly independent. So this fact that they're isomorphic lends itself really nicely to that. Coordinate vectors also allow us to associate vector spaces with subspaces of other vector spaces. So in this example, we're going to have beta be equal to the set containing B1 and B2 that are defined here. We're going to say that H is equal to the span of those two vectors. So we want to find the B coordinate vector for X if X is given here as 9, 13, 15. So essentially what we're being asked to do is to find our weights C1 and C2 such that X can be written as a linear combination of B1 and B2 where C1 and C2 are the weights. So we're going to set it up then as C1 times the vector B1, which is 3, 3, 1, plus C2 times the vector B2, which is 0, 1, 3, is equal to my vector X, which is 9, 13, and 15. So essentially what we have here then is a system of equations, and we're going to solve it by setting up an augmented matrix as we have here, and we're going to row reduce it to produce this matrix here. So we see then that we have that C1 is equal to 3 and C2 is equal to 4. So then our B coordinate vector here is the vector 3, 4. So here we can kind of visualize this. Here I have B1 and here I have B2, and up here is my vector X. And remember that our B coordinate vector for X, or beta coordinate vector, was the vector 3, 4. So our vector x here, 9, 13, 15, in R3 is associated with the vector 3, 4 in R2. So H, remember H was the span of B1 and B2, is then isomorphic to R2.